Hello, everyone. I am going to walk you through how I identified the structure of an unknown compound using spectral data. I'll be using the IR 13C NMR and the 1H NMR spectroscopy. Our unknown molecular formula listed here is C6H12O2. And by the end, I will propose a complete structure that fits the evidence that I found. So let's jump right in. The first thing I do is I calculate the degrees of unsaturation. And this will tell you how many rings or double bonds the molecular molecule or the molecule might have. The formula is here, so it is 2 times your carbons plus 2 minus your hydrogens, and this will all be divided by 2. And then here, so it's 2 times 6 carbons plus 2 minus 12 hydrogens divided by 2 will give me a degree of unsaturation of 1. Also here we can look at the number of peaks to determine the number of proton environments, and in this case there are 5. And we look at the position of the peaks to determine what kind of environments there are using our chemical shift general regions. This compound has 1 degree of unsaturation, which could mean a ring, a double bond, or a carbonyl group, so I'll keep that in mind. Next, I look at my IR spectrum here, and the IR spectrum gives you information about your functional groups based on bond vibrations. There are 2 big clues here that I noticed. A broad peak here around 33 to 2500 centimeters, which typically points to an OH stretch, especially from our carboxylic acid. And then there's also a strong peak near 1700, which is characteristic of carbon double bonded to an oxygen stretch, a carbonyl group. So this kind of tells me that I'm looking at either a carboxylic acid or an ester. Step 3, 13C NMR again. The carbon NMR gives us a picture of how many different types of carbons are present. What stands out for me, around peak 175, there's a carbonyl group around 60 ppm. You often see a carbon bonded to an oxygen, like a CH2O group in an ester. And then some additional peaks between 10 to 40 ppm are consistent with some alkyl chains, and this is leaning more towards an ester because esters have both a carbonyl group and an OCH2 or an OCH3 group. Step 4 is my 1H NMR spectrum, and the proton NMR gives us detailed clues about our hydrogen environments. I made some notes here. I talked about my ratio, 2, 3, 1, 6. This is where I got the 6 from. The integration of the peaks, which reflects the relative number of hydrogens in each chemical environment. I noticed that there was a triplet around 1.2 ppm, integrating for 3 hydrogens, a methyl group, CH3, next to a CH2. I noticed a quartet around 4.1 ppm, integrating a 2H, a CH2 next to an oxygen, a CH2O, a triplet around 2.3 ppm for 2H, a CH2 group next to a carbonyl, and then a multiplet around 1.6 ppm, integrating for 2H, likely CH2 in the middle of a chain. This points to a classic ethyl ester fragments. And then step 5, my final structure proposal. This is the information from each of my charts that I gathered, showing the functional groups, my chemical shifts, and the types of bonding environments, and the information that I collected from all of these. Putting it all together, I think the most logical structure for this is ethyl butyrate. So I see that it has my 6 carbons. I see that I have my carbon double bonded to an oxygen, my H2 groups, and my methyls here on the end. It has an ester functional group. It matches every peak in my 1R, 13C, and 1H NMR, and it satisfies the degree of unsaturation of 1. So all the data lines up with this structure. And then just some takeaways, I guess, to summarize. You want to start with your formula to calculate your degrees of unsaturation, and then you'll use IR to spot key functional groups, and then you'll use your 13C NMR to identify your carbon environments, and you'll use your 1H NMR for hydrogen environments and connectivities, and then you'll put everything together into a structure that fits all that data. I thank you guys for watching, and I hope this helped make spectral analysis less intimidating for you guys. Sure did help me.